Hi, everybody. I'm Mariel Werner, and I'm excited to share my work with you today on collaborative learning. I'd like to thank Samuel very much for inviting me to the Flow seminar. All right, so let's dive in. So the broad topic of my talk is on aligning the goals and outcomes within collaborative learning frameworks. And in particular, I'm going to be discussing a recent paper I wrote entitled Provably Personalized and Robust Federated Learning. And this appears in Transactions on Machine Learning Research, 2023. So before I get started, I'd like to acknowledge my collaborators in this work, Praneeth Karimareddy, Lieha at EPFL, Mike Jordan, my advisor at UC Berkeley, and Martin Yagi, also at EPFL. So in the standard collaborative learning framework, multiple clients collaborate to train a global model without transmitting raw data. And this scheme has many benefits. It's non-brittle. Some subset of the clients can drop out of training at a given round, and as long as a large enough fraction remain, the updates to the global model are still meaningful. It has a baseline of privacy guarantee because clients don't actually transmit their raw data in the collaborative training of the global model. And it's efficient because instead of transmitting massive amounts of data, models or partial models are transmitted in the collaborative process. However, the standard federated learning protocol has kind of an aggregation or averaging effect that yields a model that may not be suitable for individual clients' tasks, especially if those clients have heterogeneous data distributions from each other. And so this prompts the question, how can we refine the notion of collaboration so that the outcome of the collaborative process is actually suitable for clients' goals and hence incentivizes them to join the collaborative framework in the first place. So in order to set a foundation for this, let me briefly discuss the standard federated or collaborative learning protocol with which I'm sure many of you are familiar. So in federated learning, there's a central entity, generally a server, who coordinates the model updates. So at round T of federated learning optimization protocol, the server has access to a global model, XGT. The server transmits this model to N clients. And each client updates the global model with a step of stochastic gradient descent on their own data set. So in particular, each client performs such an update where eta is a learning parameter, a learning rate parameter, and here we have the gradient of each client's loss function on their training data set. This yields kind of N personalized versions or updates on the global model. Each client sends their personalized version of the global model back to the server, which then aggregates those personalized updates into a global updated model. This aggregation might look like an averaging or perhaps a weighted averaging, depending upon the size of each client's data set. So from the perspective of client I, this globally updated model will be useful for the average client. But from the perspective of some client I, who maybe has a data distribution that's heterogeneous from other clients in the collaborative system, this global model may actually perform very poorly for their individual task. And so from client I's perspective, what they really want to know is what subset of these end clients are good collaborators for me. What subset would I want to actually aggregate my model updates with, and what subset do I not want to train with, because their contributions to the global model will actually drift it away from my own optimum. And so this is the notion of refining collaboration. And this problem is referred to in the literature as personalized, federated, or collaborative learning. So our goal in this paper is to, first of all, design a personalized federated learning algorithm, in particular an algorithm that has optimal convergence guarantees and is robust to malicious attackers in the system. So the first question we need to answer is, how do we define good collaborators versus bad collaborators from client I's perspective? And how do we formally define this? And so in this paper, we observe that good collaborators share optima of their loss functions. And how do we encode this mathematically? Well, we say that from client I's perspective, client J will be a good collaborator if this inequality holds for their loss functions. So let's parse this a little bit. We say that if the norm deviation between client I's loss gradient, and the gradient of the average losses of clients who are good collaborators for client I, in particular F bar I here, is the average loss over all clients J who are good collaborators for I. And here X refers to the model parameters. So if this norm deviation, the norm of this deviation is less than or equal to some constant A squared times the norm of the square norm of the gradient of the average losses of collaborators who are good for client I, if that holds, we assume that this property holds for all clients who are good collaborators for client I. So this is basically assign some structure to the loss functions of all clients J who are good collaborators for client I. We'll see this is really a statement about it's a statement about the loss functions, but it's really a statement about the optima of the loss functions of clients who are good collaborators for client I. And how do we see this? Well, let's say that X bar star is the optimum of F bar I. Okay, so if we plug in X bar star into this inequality, this term will go to 0, as will this term. And so this inequality essentially becomes norm of gradient F sub I, X bar star squared is less than or equal to 0. So what this shows is that X bar star is also the optimum of Fi, of client I's loss function. And so what it means is that all collaborators J, or all clients J who are good collaborators for I, have the same optimum. Okay, so this mathematical property of the loss functions that we assume in our theory is equivalent to the notion that all good collaborators share optima. And in fact, there's recent work from 2022 by Evan et al. About the sample complexity in federated and personalized learning algorithms that show their theorem 1. They show that, in fact, in collaborative protocols, the optimal thing is for clients who have very similar optima to collaborate together within the collaborative learning system and to ignore updates from clients who don't share optima. Okay, so this inequality encodes our definition of good collaborators for client I. And I'll mention that this is actually once you deviate from the optimum, this is kind of a light guarantee on what the loss functions look like away from the optimum. In particular, client I's gradient can diverge from the average gradient of good collaborators for client I by quite a great degree. If you're not at the optimum, in particular, there's this upper bound on the deviation. So at this little schematic for client I and client I prime, who's a good collaborator, they have to require that they share the same optimum, but far from the optimum, their losses are allowed to deviate. Okay, so we've mathematically established our formulation for good collaborators. How about bad collaborators for client I? So we will say that client J is a bad collaborator for client I if this inequality holds. And what does parsing this? If this deviation, the norm of this deviation between client I's and J's gradients is lower bounded by this quantity, we say that client J is a bad collaborator for client I. And here delta squared and d squared are constants. So how, what does this mean? Well, let's say that we evaluate these gradients at client J's optimum xj star. I'm sorry, client I's optimum xi star. Okay, so this gradient will go to 0, as will this. And this inequality then becomes gradient fi at J's optimum norm squared is greater than or equal to this constant delta squared. So all it's saying is that the optima of optima of the loss functions of clients who are bad collaborators have to be sufficiently far apart. And so at client J's optimum, the client I's gradient's norm must be lower bounded by some constant. And so how can we visualize this? Well, in this schematic, we have client I's optimum xi star and client J's optimum xj star. And so at xj star, client I's loss function, the gradient of client I's loss function has to be sufficiently large. It has to be bounded away from 0 by delta squared. And that ensures that there's enough separation between clusters of similar clients that we can actually identify good collaborators versus bad collaborators for any client I. And note that since we can interchange the indices I and j here, delta squared just becomes the min of client I's gradient at client J's optimum squared, and the norm squared of client J's loss function, gradient of client J's loss function at client I's optimum. So that's some way to quantify what delta squared is. And so heuristically, we can think, given these two definitions, we can think of delta as a measure of intercluster dissimilarity. So some measure of how dissimilar or far apart the clusters are, and A will be a measure of intra-cluster similarity. The smaller A is, the more similar within each cluster of similar clients the loss functions are at all parameters. All right, so these two inequalities formalize our definition of good collaborators versus bad collaborators. And so now from client I's perspective, we want to design some algorithm by which they can identify their good collaborators, collaborators whose loss functions share this property, and distinguish themselves from bad collaborators, in particular clients whose loss functions have this property. And if we can do this, if client I can do this, then they can identify throughout the training process the clients with which they want to aggregate their model updates with, while ignoring the rest of the clients. Okay, so I just want to mention in our paper, we show that these constants A, D, and delta from those inequalities exist in practice, or can be meaningful in practice. In particular, we show that when we have some structure to the loss functions, so the client's losses are L smooth and mu strongly convex, and we have established that clients in the same cluster who are similar have the same optima, then these properties hold on their loss functions. So in particular, this quantity is upper bounded by 2L over mu squared times this norm. And notice this is exactly the structure of this inequality. So A squared has the value 2L over mu squared when losses are L smooth and mu strongly convex. And for all clients ij in different clusters, so bad collaborators for client I, this quantity is lower bounded by this quantity minus 2 times 1 over L, 1 plus L over mu squared times client I's, the norm of client I's gradient. And so again, if we map this onto our formalization for bad collaborators, this is the delta squared quantity, and this is the D squared quantity. So this is all to show that if we assume some structure on the loss functions, we can actually quantify what these constants A squared, delta squared, and D squared are, and they're not just meaningless or trivial like infinity or 0. Okay, so this brings us to how do we design an algorithm around these assumptions that actually gives us some optimal convergence guarantees. And so in the literature, there are many approaches to personalization, interpolation, where algorithms will interpolate a global model with local models of clients to personalize the global model, or some regularization where the individual clients' models are brought close to the model, a global model, global optimal model, by some regularization term. And a few papers have looked at a clustering approach where we're actually trying to iteratively cluster the gradients of similar clients throughout the optimization process, and compute aggregate updates only per cluster. So essentially learning a model per cluster of similar clients. So that's the approach we take. Prior to our paper, there had been very little theory, and especially the theory that did exist was for specialized loss functions. We look at a broad class of loss functions, and we achieve optimal convergence guarantees in that setting. Okay, so we take a clustering approach to our algorithm design. In particular, each client maintains its own model. And these two steps occur iteratively. So each client detects clusters. Well, we'll go to the specifics of the algorithm on the next slide, but broadly what's happening is at each step, there's a clustering algorithm that's initiated. So we determine clusters based on the gradient values of clients' losses. And here, and G is a stochastic gradient. So the expectation of G given X, given the model parameters, is equal to the gradient of the loss. And here, this little eta term is the randomness in the client I's sampling process. And so the expectation is taken over that randomness. Okay, so we cluster client gradients to determine clusters of similar clients, and then we aggregate the models per cluster to progress through the optimization. So in particular, if client I belongs to cluster CK, then the update of client I's model will look like this. So there'll be some step of gradient descent using the aggregated info of all clients within cluster CK. And something to note is that we assume the number of clusters, so K, is known in advance, and this parameter could be learned throughout the clustering and optimization process, but in this paper we assume it's known in advance. Because the thing is that this procedure is hard to do while optimizing, because notice that our constraints on good and bad collaborators were really only constraints on the optima of the loss functions, and we were quite liberal in what could happen as you deviate from those optima. And so let's say at some initial point of some model initialization x0, let's say it's maybe over here. So clients initialize their models here. Well, it's possible that at this point, client I's loss, gradient of client I's loss, is actually very similar to the gradient of client J's loss. And so even though I and J belong to different clusters, maybe at initialization, their gradients are very close. And so as we cluster the gradients in this step, early on, it might seem that clients I and J belong to the same cluster. And so obviously they're distinguishable as you get close to the optima, but depending upon the loss functions, for instance, if they're not convex, which we don't assume in this work, it's possible that the algorithm will detect I and J as belonging to the same cluster early on, and will update client I's and client J's models in ways that will deviate from their optima, and we won't have good convergence guarantees. So it's a hard problem to essentially iteratively identify clusters and optimize. And so our key to working around this will have kind of a very rigorous identification process throughout the algorithm, where we very carefully try to identify which clients belong together, and in particular have an infrastructure of clustering that if mistakes are made, that's robust to mistakes. So if mistakes are made, clustering mistakes are made early on, they could be corrected later. So precisely what is the procedure of our algorithm, federated clustering? So at round T, each client has their current model x sub I t minus 1, their local model. They broadcast this model to all other clients J in the collaborative system, so set of n minus 1 clients. Each client J computes their own gradient on their own data of client I's model. They send this gradient back to client I, who then clusters all of these gradients. So essentially clusters the gradients of all other clients at client I's model xit minus 1, initializing the cluster center at client I's own gradient at x model xit minus 1. Perform this clustering routine. They identify some point, the output of this clustering routine v sub it, which aggregates the information from all of those gradients. And ideally, v sub it will be some centroid of the gradients of clients that client I thinks are good collaborators for it. And using this quantity v sub I minus t, client I will perform an update on their own model. Each client in parallel does this in the protocol. And so by the end, we have n models, and ideally these models will reflect the collaborative updates of clients who are similar to each client I. This is a collaborative learning. Notice this is a collaborative learning algorithm, not specifically federated learning. We don't have some central coordinator, but later on in the paper, I won't go into that detail in this talk, but we provide a momentum-based version of federated clustering in which a server, a central entity, coordinates the updates and the communication between clients, which makes it more communication efficient. But just because our main contributions in this paper are theoretical, we'll discuss sort of the fully specific version of this protocol, federated clustering. Okay, so what is this clustering algorithm? We identified before the challenges of iteratively clustering and optimizing. So how is each client aggregating the gradients from the system in a way that's robust to mistakes and can easily correct mistakes? So our clustering routine is the following. Client I at step t has its own gradient g sub I at its model x sub it minus 1. And it also has access to all the other clients' gradients evaluated at its model x sub it minus 1. So what it's going to do is just going to execute a clipping procedure. So it's going to, client I will initialize a ball of radius tau sub I at its gradient. And it'll see which other clients' gradients fall within that ball and fall outside. Clients' gradients who fall within the ball will retain their value, and clients whose gradients fall outside the ball, their values will be mapped to the center of the ball. And then those values are all averaged. So this is what this sort of unwieldy expression is saying, but it's actually very simple. It's just saying, okay, if a client's gradient falls within the ball, so the distance between its gradient and client's I gradient is less than or equal to tau, then keep its value. If a client J's gradient falls outside the ball, then map its value g sub j to client I's gradient g sub I. Sum up all those values and just average them over n. So what is the effect of this clipping procedure and why is it robust? We'll get into the kind of the technical guarantees of robustness later, but just intuitively, let's say a client's gradient falls very far away from client I. Well, client I's gradient, well, client I is not going to want that gradient to influence their own update. It likely belongs to a bad collaborator. And so the value of that gradient will just be mapped to the center of the ball and will have no contribution to the update. Meanwhile, clients whose gradients are close to client I's gradient will have an impact in updating client I's model. The radius of this ball is key for achieving the convergence guarantees that we want. And so in particular, we define the radius of this ball to be within a constant value of the square root of n sub I over n, where n sub I, little n sub I, is the number of good collaborators for client I, times sigma, which is the standard deviation of gradients, client I's gradient, and delta, which remember is that kind of measure of intercluster dissimilarity. So essentially it's not exactly this, but heuristically you can think of it as sort of like a distance measure between the optima of different clusters. And so the formulation of tau is important because if you think of sigma as kind of some measure of deviation within the cluster, and then delta is some measure of distance to the next cluster or to different clusters, then tau here is a scaled version of the geometric mean between those two quantities. And so recall that how I mentioned that if depending upon the initialization, it might be hard to actually identify good collaborators early on. You might think that the bad collaborators belong in your cluster because loss functions, we don't have too many assumptions on the loss functions away from the optima. And so from client I's perspective, they're at round 0 of optimization. They want to be liberal in they don't want to exclude clients who might actually be good collaborators just because their loss functions look different at the initialization point. And yet they don't want to be too inclusive and include all the clients because then they'll have bad collaborators in their updates. And so by taking the geometric mean between sort of the intra-cluster distance and the inter-cluster distance, we achieve a middle ground between these two things. And this makes our algorithm robust to mistakes, and it also accounts for the fact that far from the optima early on in the initialization procedure, it might be hard to actually identify clusters. So we set this radius to be geometric mean between kind of the intercluster distance and the intracluster distance. I want to mention that at each round of optimization, we kind of run this clustering procedure multiple times until VIT, the center of the cluster, converges to a fixed point, roughly to a fixed point. And here's a kind of empirical tracking of how many rounds, how many clipping iterations it takes to do that as a function of the standard deviation within each cluster. So obviously, as the standard deviation increases within each cluster, so it's harder to identify clusters of similar clients because their gradients have a lot of variance. It's going to require more kind of clipping iterations to converge to some stable center of the cluster v sub it. But the number of clipping iterations sort of scales with log, scales in this way with the number of with the standard deviation. And that's exactly what our theory shows. We show that if log is greater than or equal to this the number of clipping iterations, L is greater than or equal to this quantity. So we have this log sigma scaling. Then we get a nice convergence rate that that includes the quantities, important quantities in the problem. So in particular, the more clients there are within client I's cluster, the easier client I's clustering task will be. The greater the distance there is between clusters, the easier the clustering task will be, and the greater the variance within client I's cluster is, the harder the clustering task will be. Okay, and then this term accounts for the error in our thresholding ball. Beta I is a parameter, our robustness parameter that I'll discuss later. But all this to say that the clustering task becomes harder as standard deviation increases, but it scales with log as log in that term. So it's a manageable task. Okay. What are the convergence guarantees of our algorithm federated clustering? Well, we have that for each client I with L smooth loss, so no assumptions on convexity, just smoothness, this rate, convergence rate holds. So in particular, the average of the expected values of the norms of client I's gradient at each of its model updates throughout the algorithm is less than or equal to within a constant factor this bound. So let's parse and discuss how the parameters of our problem factor into this bound. Sigma squared is, as I've mentioned, the variance of client i's gradients. Sorry, an upper bound on the variance of client I stochastic gradients. N sub I is the number of clients J who are good collaborators for client I. And as we saw in that early slide, this is equivalent to all clients J who share client I's optimum. And beta sub I, which is a term we haven't discussed yet, is fraction of clients malicious to client I. So we permit in our problem setting that some fraction beta sub I of clients are malicious to client I. They're deliberately trying to make client I's learning task harder. And we do experiments, formulate experiments with various kind of malicious objectives by these clients. Okay, so how do these terms factor into the rate? Well, first of all, we have order 1 over square root of t, optimal convergence rate for stochastic gradient descent on non-convex functions. So that is good. And then the convergence slows as the stochastic variance as stochastic gradients increases. So as it's harder in the clustering problem to identify clients with clients who are good collaborators for I because there's high variance in their gradients. Convergence speeds up as Ni, number of clients who are good collaborators for I, increases. More clients in the system who are good collaborators for I, it's going to be easier for I to identify those and update their model in an impactful way. And then convergence also slows with delta, which again is this measure of, convergence speeds up with delta, which is this measure of intercluster dissimilarity. So the more distinguishable the clusters are, the greater delta is, the easier convergence will be, or faster convergence will be. And then we have this term beta I sigma delta. And so what's the significance of this from a robustness perspective? Well, recall that tau sub I was the radius that client I, when clustering, constructs around its gradient. We had this tau sub I radius. And tau sub I was order square root sigma delta, so the geometric mean between kind of the intra-cluster distance and the inter-cluster distances. And so what is the worst thing that a malicious attacker from client I's perspective can do to affect client I's convergence? Well, the worst thing they can do is assuming that a malicious client can just arbitrarily set their gradient. Well, the worst thing they can do is set their gradient to be a value that falls right on the boundary of this ball. And why is that? Well, because given how our clustering rule aggregates the gradients of all the clients, if a malicious client to I wants to affect the update on client I's gradient maximally, they should put their value somewhere on the radius of this ball, because then client I will factor the true value of that gradient into their update, and the further away it is from all other from client I's gradient, the more of an impact it will have on client I's update. If they position their gradient outside this ball, then well, that value is just going to be mapped back to the center, so it will have no impact. So the worst thing a malicious client to I can do is arbitrarily set their gradient to be right on the boundary of that ball. And so that's exactly what we see here. Sigma delta is the square root of sigma delta is the radius tau sub I. And so that's scaled by the fraction of clients who are malicious to client I. as if no clients are malicious, that this term will just go to 0. If there's a large fraction of clients in the network who are malicious to client I, then that will potentially slow the learning rate by a factor of this sigma delta, square root of sigma delta, which is the length of that radius. Okay, and a squared here, in the details of the paper, this is really just a max of 1 in a squared. But all to note that a squared was kind of a measure of away from the optimum of clients in a similar cluster, how far, to what degree their losses deviate. And so the more they deviate away from the cluster optimum, the harder the learning task will be for clients within that cluster. The closer it is to 1, the easier it will be. Okay, so that's our convergence results. And yes, these are for personalized collaborative federated learning, these are the first optimal, or for first convergence guarantees for non-convex smooth losses, particularly their optimal rate in T. And they have nice properties in the other parameters of the problem. And this holds per client. So not over the average of clients in client I's cluster, but for each individual client I, this rate holds. Okay. So briefly discuss the empirical performance. We apply our algorithm to a couple of tasks, in particular a rotation task and a corrupt label task. And we specifically designed these tasks so that personalization is critical. One thing we do, for instance, is for a rotation task, we define 4 clusters, k equals 1, k equals 2, k equals 3, and k equals 4 for each image MNIST, and rotated the label for each cluster. And then we also have this corrupt label task where for the same image, different clusters will label it differently. So for instance, cluster 1, given this image, is going to assign a label of 4 to that image, but cluster 3 is going to assign a label of 7 to that image. So we have some kind of label mapping according to this mapping. And so we have in the training data across clients, you have the same image that has different labels across clusters. And so if we were to just apply a standard averaging, a Fed average, standard federated learning protocol to this, we would get very bad results because, for the same label, for the same image, there are multiple labels. So it's very important to identify the clusters within which the label for each image is the same, and only have those clients collaborate in creating a personalized per cluster model. And so we compare our algorithm, which is FC, federated clustering, to just local training, so training alone, global training, which would be Fed averaging, so where just all the client models are averaged for the updates, and then a variety of other algorithms in the literature, ditto IFCA and KNN. These are, IFCA is another clustering algorithm. Ditto and KNN are both are regularization, and they're both interpolation algorithms. So they interpolate between the local model and a global model. And so we see that in our results that this is Yeah, you can see it here, that on these tasks, all algorithms that are incorporating information from just a global model that's kind of naively averaged across local client updates does not do well. So our algorithm does well on these tasks, but for instance, global model does quite poorly, which is just creating this global model, Fed average model, and as do other algorithms, for instance, Ditto, which and IFCA, which are using information from global model as well. The same here on CFAR 100, we see that our model outperforms global Fed averaging on these tasks where personalization is very important throughout the training process. And just a note about our robustness algorithms, we ran experiments on large gradient and bit flipping settings, so where clients could arbitrarily set their gradients to be very large, or just arbitrarily flip the sign of their gradients. And our algorithm is robust to those kinds of attacks. It's easily able to identify due to our clustering algorithm, or essentially due to our clustering algorithm, mitigate the effect of those tasks on individual client updates, whereas a global Fed averaging algorithm does not mitigate the effect of those attacks. And so this is empirical evidence for the robustness of our method. That concludes my talk. Yes, please feel free to reach out if there are any questions, and full details in the paper can be found in our version on arXiv. Thanks very much for the opportunity to share my work with you.